All right. So hello, everyone. I am Jean-Yves from the Digital Universität and NHR at the Digital Universität, and I'm presenting today the ParaViz3D program. It's an MPI trace visualization program with 3D animation. So I'll first talk about the theoretical problem and introduce you with what will be discussed in this presentation. So first of all, I'll talk about trace data. What is trace data and what is its traditional display? And I'll talk about the limits of this display and how we propose to improve it. We are going to see our results of our visualization method. And I want to say that this is a work in progress and that it's changing rapidly as we speak. So first of all, trace data, the use program that we use to our test cases is Jacobi codes. I'm going to introduce Jacobi codes shortly too. Generating idle waves, I'm going to explain what they are. And I'm going to do that in different run conditions and in different domains. So just a short introduction about trace data. Most of you already know what it is, but I'll just, as a quick reminder, explain what it is and how is it used. So tracing is a systematic log of the events of a program's execution. It's essential to understand, to compare, and to investigate programs. It basically is a list of timestamps of the regions, which is the special name that we have in tracing to talk about functions. Every time you go into a function, or every time you leave a function, or rather a region, it's the correct naming for that. Well, you're going to have a record of that, and it's going to be recorded into what we call the trace. This list of timestamps, if we look at the trace without a display, it's hard to picture because it's just a list of timestamps, and we need to have proper visualization for easier comprehension. And for that, the tool we used is called ScoreP, which outputs in the OTF2 format. It's a well-known tool. The traditional display for this ScoreP tool, which only does the tracing and the recording, is basically an image, still image, which is going to have as output a vertical axis for processes or for MPI ranks, and a horizontal axis for time. It's going to be color-coded rectangles for each region. And it's a great help to have a visual representation and to see synchronicity of the events and time-related phenomena. That is an example of Vemper, which handles OTF2 traces. And from that, displays the output, as I said, with ranks being sorted in the vertical axis and time in the horizontal axis. You see those rectangles, and you see even the names of the regions. In red, you have the MPI events, which are the communication events, and in green, you have the computation events. When a rank is sitting in MPI, it's going to be displayed in red. And when it's not sitting in MPI, it's going to be displayed in green. So what are the limits of this traditional display? Well, first of all, many programs adapt to their problem's geometry. And when you have only a one-dimensional program underlying geometry, well, that's okay. You have something that's consistent. It's easily shown by this traditional display. But what about grids, or tubes, or spheres, or even more complicated geometries? So contiguous rank in the domain and in the communication schemes, they are often separated because of this problem's geometry that is unlike the line, the 1D geometry. You are also unable to display, understandably, too many ranks. And there are many other subtleties that I'll give examples to later. So which program was used for our development? As I said, we used Jacobi code. And the only or the most important thing that you need to understand about the Jacobi code is that every rank will regularly meaning after every loop, will need to communicate with its direct neighbors. We always inject at some point an extra workload on rank 5, and this extra workload is used to have some sort of a load imbalance. Therefore, its neighbors need to wait for that lagger's communication because of the extra workload. It's going to finish later, and in turn, their own neighbors need to wait, and that's creating an idling for all those processes, and this idling is piling up as processes wait for their neighbors, and then their neighbors wait, and then their neighbors wait. Once rank 5 finishes and communicates, it's what I call the bubble bursting. It finishes, it gives its output, and then the neighbors can finish and give their own output. This creates a ripple effect of idling processes that is called an idle wave. I will show visual examples of that later. This is a 2D display of a 1D idle wave. As you see, you have the rank 0 that has an extra workload. And in purple, you have the delay because the neighboring rank needs to wait for rank 0. And so on and so forth with rank 2, 3, 4, 5. So these are two different examples of that. The requirements we wanted to have for this display that we created. Well, first of all, it needs to generate videos or animations. One advantage is that it frees up the time axis. It's not only because it makes it more understandable, but it's also because it's a straightforward representation of the data, and that can be the case for up to 3 dimensions without cuts or projections. So we initially used Blender and coded with Blender to generate this display, and we later used the browser display. We also created a Python script to parse the OTF2 trace and to filter that trace. And we explored smart ways to display traces in the most intuitive and understandable ways, using different colors, using transparency, and using some specific geometries. The testbed is not so interesting, I think, to most of you, but I'm just showing it shortly. We use the Fritz computer nodes, and it's just some regular CPU supercomputer nodes. Nothing too interesting about that. And then here's a screenshot of the results. So now I'm going to show an animation of it. So here you see the Jacobi code that we coded, and this is a square geometry. And you see that in this display, everything that's transparent is not sitting in MPI, and everything that's not transparent is sitting in MPI. The ranks that are sitting in MPI change their colors from red to green as they go from the beginning to the end of the MPI process. And you see this piling up, with rank 5 having an extra workload, it's transparent because it's computing, and then every rank around it pile up. Then it finishes, the bubble bursts, it communicates to its neighbors, then their neighbors communicate to their neighbors, and you see that idle wave travel. It crashes then against the other side of the idle wave. I'm just going to quickly let you show this, and I'm going to, after that, show you the Vemper display to this particular run. So you see, just take a quick note about the fact that all those ripple effects, they seem kind of horizontal, which is not necessarily very intuitive because it's a completely square domain. I'll get back to that later. All right, I'm going to speed up a little bit. And in the end, we have MPI finalized. All right. So here is the corresponding Vemper display. You see all of the ranks. There are 568 ranks. And you see that kind of arrow shape. You see a lot of them. And they come at some point after in rank 5 up there has the extra workload. You see the green part, green line, and that's the extra workload that was injected. From there, there's the red parts around it in an arrow shape, and those are the ranks that are waiting for it. The thing is, in this representation, you may be under the impression that there are actually several extra workload injected and several idle waves that are generated because of those multiple arrows. This is actually what I talked about earlier about the geometry of the problem that makes it less understandable to have that kind of display. Here, even some trained eye could be fooled by that. It is actually just every 24 rank that you have this kind of every arrow is of size 24 ranks because it just so happens that the square domain has a 24 MPI rank width. And this is the reason why we have this many arrow shapes. The actual idle waves is the general arrow here that you see, and that takes up all of the trace image. This is the actual unique idle wave. So I'm just going to quickly introduce to the tools usage and present you the steps that were necessary to use this tool. So the Python script that was used allows you to go from a Scorpy trace to a ParaViz3D file or ParaViz3D accepted file. We provide a Python script first that reads through the trace and then sorts accordingly and aggressively filters it. It outputs to a text file that's 100 times smaller, which is very important to be handled to fit in memory. And this scheme allows for big traces to be handled. I'll show you a demo. Okay, so just a second. So here's a typical Scorpy trace folder. You have Scorpy traces with events, files, and then you also have, where am I? Is it this one? Yeah, and then you have definition files. event files and definition files. And then these are holding the data in the Scorpy format, the OTF2 format. This is the main file. From there, you're going to have this trace converter Python script, and you're going to indicate it the root folder and some options. And then it's going to have the parameters printed to you. It's going to be checking if you already run the script, and then if you want it, you can overwrite or not. So select yes. And of course, I have a problem because probably like, all right, well, I must have selected the wrong folder. In any case, after that, you have another a generated file. Those are the files that are generated, which hold the data necessary for handling the trace in the ParaViz3D format. Once you feed that into the program, I'm going to first show Blender. You have this visualization. Here's the beginning time, and then you can play it. You can go further away, faster, and you see that same tidal wave being created. And you can go back in time. All right. I'll show you other examples for other geometries. So we generated some YouTube videos holding this visualization. And another case was a cuboid idle wave. I think it's okay now, yeah. All right. So as you can see, you have that same kind of heartbeat fashion lockstep condition, and then you have an idle wave that's generated. The extra workload is up there on the upper left, and then you see that it's rank 5 finishes, it bursts. And what you can see is by going through a special part, taking a special angle, panning, zooming, rotating the appropriate way, you see computational wavefronts that have a specific direction. That's an interesting fact that you may want to explore, and that may be useful. That's one of the more interesting and a little more subtle cases that you may find useful and that you may benefit from with this kind of visualization. Let's go to another test case. Before that, I'm just going to show the corresponding trace data, if I can. Just a second. Hopla. Here you go. So you see that idle wave is also there, and it gets, as the geometry gets more complicated, it gets more complicated to understand what's there and what we see. If you were to be able to see the direction of the computational wavefront, that would be very hard to see there. And it's something that I could see only after I was able to use my own visualization. And that's how I could see that it's actually possible to see it from the 2D traditional trace display. Then we went to a third case, the sphere case, that I'm going to show now. So again, there, you're going to have rank 5 that has an extra workload. It's highlighted right now. And you see processes piling up. Until the bubble bursts. All right. Let's go to the end. And then in the end, the computation ends with the last ripples. All right. And now let me show you what it looks like in the trace. This trace is completely ununderstandable for me. I don't see any pattern here. I don't know what happens. And this is heavily linked with the fact that it's a sphere and that showing rank from 0 to max is not the best way to show the data, and it's not going to show you which are the neighbors you communicate with. If you have a custom communication or a complicated communication due to the geometry, my tool makes it way more understandable to see what happens. This is one example for that. There could be many others. Keep in mind that we stayed with traditional domains, such as a square, a cube, and a sphere. These are the most simple, right? So, as I showed the results, here's a comparison of the two different views. And we've tested in the beginning red for MPI, then blue for computation, then red for MPI, and transparency for computation, plus some sparsity in the 3D grid in the cuboid case. And we've shown using, as you just saw in the videos, a gradient that is progressively going from red to green over the span of the MPI regions. In the end, it comes down to the user selection, and we want to be able to adapt to that. So the tool advantages, as I said, it's that 2D and 3D domains are accurately displayed. It's a more straightforward and intuitive presentation of the trace. And it's a faster and finer comprehension of the program that is being traced. So how can we improve it further? Well, we can develop additional metrics that I can show you a little later, and some statistics that are shown in 3D. We can make them customizable by the user and preferably on the fly. We can support custom shape and meshes, including unstructured meshes. We want to be able to use VR headsets for real 3D with different displays for the two eyes, and to be able to travel through the trace, so to speak, or through its 3D representation with live rotate, zoom, and pan. We also, of course, wanted to make it lightweight and scalable. And we will end up using JavaScript to display over the browser. This is something that's already begun. So let me show the current work, which is the browser output. Oh. Oh. All right. So this is the current representation, and the current tool as is being developed with browser. So the first step is to download the script, Python script, and then using it on your trace. And if you don't want to do that, if you just want to test the tool, you can also select an existing example trace that is made available for you on the server. So let's take the square case. And then you have some other options. First of all, you can hide or not the coarse outlines when they are transparent. You can select the geometry. Let's take, so it's a square, but I'm going to take a cuboid with a only one rank on the third axis. And then I'm just not going to show the machine topology. I'm going to explain later what that is. You have some advanced options. It's just for the rank shape and some sizes of the figures that are displayed. And then you have the desired metric. So dual view will make you able to have two side-by-side views. If you want to compare, for example, MPI regions and to color them in a certain way, and computation or out of MPI regions. Let's take the example with a single view of colored MPI times. We're going to use color gradients as we did, and then we're going to select the color. So the color we're going to keep the same, red for the beginning of MPI. We're going to put green for the end, and we're going to put transparent for the computation. And then we can include the traditional Vamper-like view. Some of the controls are the time granularity, if you want the time to go fast or not. The playback speed is for if you want to go the time to go fast or not, and time granularity is going to be the number of cycles you skipped at every frame. I'm not going to show that right now. And then I'll hit visualize. All right. And then let's click that to have only the display. So here you can see that it's the same display as originally shown. And we can rotate to it. And then we can play. And while it's playing, I can rotate it. and pause it, go through the next or the previous frame, and I can go through whichever part of the trace. Let's take another example. We're going to take the cube case. We're going to do 6 by 12 by 12, which is the corresponding geometry. We're not going to include the traditional vector view. Then we're going to hit visualize. And you have that same cuboid that you saw earlier. I'm just going to go fast on the MPI init that wasn't ignored here. And then this is the actual computation. And you see it. And just an example here, when you see those heartbeats, those waves of communication, when the parts, this is the part of the ranks that are still in lockstep, because the idle wave hasn't reached them yet. It seems that they have some sort of spherical shape, or maybe cylindrical shape. That is not by chance. That's because in this case, contrary to the square case, I didn't activate periodicity, which means that the boundary ranks are not in communication with the other side. They are only in communication with their neighbors, but they are not going to be all having 6 neighbors. Some of them have only 3 neighbors, the corner ones. And this makes them have less communication to do. They have less waiting to do, waiting to receive their neighbor's computation. This is something that, another example of thing that you would be very smart if you saw that in the traditional trace. And then you can select some of the lighting. This is not so important. This is just user selection. All right. And then I'll just show one last example. And those cube 10, cube 50, cube 60, cube 80 are attempts that we had for scaling tests. So basically, I took this cube trace and I reproduced it 10 times over, or 50 times over, 60 times over, up to 80 times over, to see how many ranks was the browser able to handle. And let's see that. I'm just going to match with a 60 rank first axis dimension, and then I'll see how it goes. And maybe I'm just going to change the color just to show. Let's visualize that. All right. So I have 10 times as many ranks. And of course, it's not so significant. It doesn't mean anything because I just copied over. It's not a real computation. But as you can see, it works smoothly and without needing any more than the browser and your own computer. That doesn't need to be very powerful. I think it's possible that even your phone could be able to handle that. And you see this computation finishing. This WebXR not available there is because I'm using a computer instead of a VR headset. And because of that, it is just telling me that it cannot handle a VR display. If you use it with a VR headset, this is going to be changed into go in VR mode. And this is under active development too. All right. So I will be welcoming your questions now, and thank you for listening to me. Special thanks also to Georg Hager and Aisha Afzal, which were my advisors for this development.
Okay, thank you, Sharif, for this very interesting and colorful and exciting presentation. Do we have any questions? So far, I don't see anything in the chat, so you can either put questions in the chat or raise your hand and unmute your phone to ask the question directly. So while people are thinking about it, let me answer ask a general question. So your tool is basically visualizing MPI calls. Is it restricted only to messages, or do you take into account like also collective operations, file operations, basically every MPI function?
So that's a good question. I want that to be, so the first work that we did was to, of course, focus on the MPI calls. First of all, it's not an obligation. It's just that it was the most interesting test case for us. We could select a particular call by its name, basically. But we color every MPI call, which have the particularity to all begin by MPI or MPI underscore. We color them with that scheme that we showed earlier, which is that it's going to be colored instead of transparent, and that it's going to go from red to green. But of course, we could focus on collectives, and this is one of the things that I wanted to develop and that I'm developing right now. I think you saw it.
Yeah, basically that was the background of my question, because I can imagine that if I have like point-to-point communication with specific communication patterns, yeah, which kind of implement this wavefront and stuff like that, you see specific things, but like file I/O or collective operations may behave differently and might require different kind of visualizations, not just like the red to green or something else.
Absolutely. So in our metrics, we have different things that are available. Some of them are not developed yet, but some of them are. And sometimes you want to focus on MPI, but sometimes you want to focus on out of MPI times. You also may want to have heat maps showing speeders and laggards. You may want to see what's the instantaneous speed in MPI or not. And you may want to distinguish the sends, the receive, the wait loss. With all of these, you may want to include the traditional VM purview or also exclude collectives or point-to-point, because that's your focus. This is one of the this is the even more interesting visualizations. They give you even more insights, and I could show you some if you want some of those metrics. I have videos available and ready for them too.
Yeah, not for now. I think we have now some more questions coming in, but as you said in the beginning, it's like this is really work on progress, and it's really exciting, and it looks like it has a lot of potential and other things coming up. So Christian from Darmstadt is asking, did you investigate to plot communication in your graphs? Like
Yes.
plot who is communicating to whom, how much bandwidth, and things like that.
Yes, and I did it. It's a little more complicated, but it was. I didn't make it a priority because a lot of the things that I saw with it were already showed or obvious from the already existing scheme. I do have some beginning of visualization for that. Let me just, I can show it very quickly. So this is an example of it. You see the arrows. It was just a try with it. And you see an idle wave too. And every time the tail of the arrow is lighting up, let me pause right there. Every time the tail is lighting up, it's a send. And every time an arrow is lighting up, it's a receive. Then the continuation of that was to have only one full arrow that would be going from red to green instead of just some burst of light there, because it was more useful to do that. But even then, it was just not that interesting in itself. For my computations, just for my test cases, idle waves, they were already shown. It was not adding any more information. But of course, I will be handling that. And I will be also handling some metrics such as bandwidth, but not only that. I would also like to have a number of messages handled, not just data transferred or stuff like that.
Okay. Then we have actually two questions going in the same direction, one from Ananya and one from Pavel. Is it possible to label or identify ranks? Yes, like if you say like this was rank number 5, and how is there a way to interact with
So yes, I have hover info options down there, and when you hover over a rank, you will have the rank name displayed if you selected it. That's already the case with the Vamper view. I wanted to hover over a certain part and be able to display, I think you might have seen it, be able to display which MPI call is the one that you hover on. But yeah, it's going to be an option. It makes it a little less scalable. I can handle less big traces, but this is, I'm hoping to be able to make it almost as scalable as without it.
Okay. And then there's a correlated question. Yeah, it looks like it's very well working with regular domains, like 2D, 3D things. Like, what about higher dimensions? Yeah, someone is doing some encoding of string theory with 11 dimensions or something, or some totally like unstructured, whatever, more like a graph or a tree or something. I mean, of course, it can be also visualized, but have you experimented with more unregular topologies?
So the most unregular topology that I have a visualization for is the sphere, but my next goal is to handle unstructured meshes. So basically, I even made actually a chessboard, and I wanted to color the chessboard accordingly to just a square display, and to subdivide that chessboard into a 24 by 24 grid, so that I could light up the chessboard as if it had been computed by a 24 by 24 grid by 24 times 24 ranks. Of course, this was just a way to test that I could handle it. And I wanted to have true research and a true program that was really outputting to an unstructured mesh. This is why I contacted TU Dortmund. They have a very interesting code. And one thing that's very interesting in their codes is that they already have submeshes, because the thing is, if I want to be handling meshes, well, I'm going to need to know which part of the mesh was handled by which MPI rank. They already have that. They are generating submeshes, and they have the same. The only thing that I need after that is to have for all those meshes the same origin point, so that they perfectly aligned with each other, and then I can light them up accordingly to their MPI rank that generated them, or that computed whatever they needed to compute regarding this zone of the mesh. That's going to be handled, and also, of course, custom shapes. I already tested giving a TXT file of another format, of course, that would be basically saying what is the location of each MPI rank ordered from 0 to max. So yeah, that's those 3D domains. They need to be as customizable as possible, and this is going to be handled too. The next thing would be to be able to handle, because of course I can only show up to 3D shapes, so I would need to have something that adapts to. I mean, if you want, for example, to project a 5-dimension figure onto a 3-dimension figure, well, you could do that, and through a projection. So you would need to project two different axes, and that's one of the options that I intend to develop.
Yeah, we have a feature like this in Cube, which also allows you to visualize profile data in a 3-dimensional way, and then we kind of also splice or project multiple like you can fold a 3-dimensional array in a 1-dimensional vector. Basically, you can do the same thing for higher ones. The problem is like if I have some meaning in the 3D. Yeah, when I can see it, but now when you have some meaning in 6D, but you basically merge it into 3D, you lose the meaning. Yeah, you don't see the neighbors anymore. So it has its yeah. I guess our brain is not built for beyond 3D, at least not for me.
But it may be the case. It very probably may be the case that you are still going to be able to see some patterns. I mean, if you project a 3D cube onto a 2D square, let's say there is some spherical shape communication patterns, well, you would still be able to see a circle. Here you can see in the geometry section that I coded, or I will be coding, and I intended to code for a hypercuboid projection. You have the problem dimensions, which is 4, and the output dimensions, which is 3. So basically, you have to select which dimension you project and which level, which means like which every rank has its own coordinates, and you need to select the coordinate in that dimension of the projection. That's just an option.
Okay. There's a final question here. What is the largest trace you could visualize and explore? I think you had one example here, so that was 10 by 10 by 100, or what was that?
So I intentionally used a shitty computer, and I failed to have 80 times my cube, which is my cube is 6 by 12 by 12, so it's basically 864. 80 times failed, 50 times it was okay. So 50 times it's over 40,000 ranks. It's 43,200 ranks. This is the maximum I had with a shitty computer. If you want to go to 64K ranks, it's very probably going to be possible with a computer that's a little more than shitty.
Okay, thank you. Yeah, like one final kind of comment or question for me, be like working in that area for a long time. If I have like a very long recording, I somehow, if I do an animation, I have to sit in front of it and watch it carefully. So I cannot I mean, I can stop, go in and watch it, but I have to carefully watch when if there's some, whatever, after 8 minutes, there's a 3 minute, a 2 second or 3 second weird change which encodes some error. Yeah. Like if I don't look carefully, I can easily miss it. So in a more static display like Vampire,
You can
I still
zoom,
can
yeah.
get lost or something if I get to zoom in at some point. But like both of these, yeah, the longer and more complicated the visualization, the more easier is it to overlook something or something.
Yeah.
So,
So
do you envision whatever potentially using AI to detect unusual patterns and highlight them automatically, or do you have any ideas how to handle this huge amount of data and but find the right stuff in it? It's a
So
problem.
using AI or other stuff to recognize or to intelligently try to find some meaning inside the trace is not something that was in the scope of my research. Although it was definitely talked about, and we had discussions about that, several discussions about that. I think displaying a good visualization for the human brain is already very good, and actually the best progression. It's the name of the game, and anything over that would need that to be first perfectly done, I would say. But if you want also to see, I think that was also the meaning of your question. If you want to see some trace events that you may have missed because they were the trace was parsed into in a too coarse way and looked over those tiny events, that's something that you will be able in the end, you will be able to modify through the time granularity, and essentially you will be able to modify a little bit as if you zoomed into the trace, and it's what you do in Vemper, so that you would be able to see in the video or in the animation some faster events that would be way quicker or even ignored, overlooked because they are just too quick for too coarse parsing. And this is what I mean by time granularity. Of course, this tool is going to be accompanied with a documentation to explain more than with just 2 words what every option does. But yeah, that's what I intend to do with time granularity. I just want to quickly address some other things. For example, identify the rank, which is responsible for the wave. This is also related to the question before, as identification, smart identification of some schemes. This is something that's not in the scope of my project, but it's definitely something that would be very interesting. Also, some how do I deal with the 3D domains with, for example, 11th dimension string theory, uh, folding and slicing. This is not something that I intended to do. It's interesting. I haven't given much thought about it. I don't know, maybe in the future. And is there a way to couple this visualization with the performance data delivered by Scorpy and Scala? Well, Scorpy is not a display tool, so I will talk about Vampire instead. And yes, there is a way to couple with Vampire or the traditional view, the Vampire view, as I showed here, would include traditional Vampire-like view. So yeah, there will be a way. I'm hoping to make that as straightforward and as easy to manipulate as possible. And thank you for every question. I think that was the last question.
Yeah, I think we also basically have an hour now, and this is a
Yeah.
perfect time. So thank you again, Jean-Yves, very much for this very exciting and promising new work. And I think it's always good when lots of new and additional things can be built on. It's a sign of good work, and there's a lot of interest. So thanks everybody for joining today. And yeah, that was the 39th pop webinar.
Thank you very much.